Chem 152 to Chapter 7. A couple things to note. The Chapter 6 homework is due on Thursday. Let me know if you got questions on that. Chapter 7 is due after spring break, and I will have office hours using Zoom Tuesday, Thursday, 9:35 for a lecture. Spring break is as scheduled, and then quiz 3, exam 2 will be after that. Before though, need to really get your attention, check your email, go to Canvas, but activity 2 is due on Friday. I don't think this should take you very long at all, but it really will get you familiar with what you're going to be doing for quizzes, exams, how to upload a document that's one PDF. I'd encourage you also get started on those solubility rules. Those are posted on Canvas now as well. So we got a lot to talk about today. You've been doing a lot of this already in lab. You've been seeing some great chemical reactions. Now we're going to go into great detail. What do we do with these chemical reactions? How do we represent them? What are some new definitions, new things to talk about? And then there's going to be the break. Okay, so my concern is we typically have exam 2 before, and that's what the schedule was, before break. So I hope you can use the break, get adjusted, so then next week when we come back, you can get back in a routine, get in a groove, start getting ready for the exam. All right, so what we're talking about are chemical reactions, and you can see here, maybe even back to the science fair days. These are really interesting, really enjoyable to see. You've seen some in lab that have been, produce solids, or that produce, heat, or they cool. So lots of things can happen when we're talking about chemical reactions. So, of course, chemical reactions are a really big deal. They're used for energy, used for transportation, used to do things clean. If you're eating, you're drinking, you have chemical reactions going on in your body. So this is a real important thing to understand, and then how to represent that. How do we represent these chemical reactions? What's going on with the matter? And that's what we're going to see, as you've already seen with these chemical reactions, an arrow. Something's happening to the matter. Something's changing. So one example is octane. It's a component of gasoline. It reacts with oxygen and forms carbon dioxide and water. So again, a single arrow. These are reacting, and what's ending up are our products here. That's what's happening. So that's what we're going to work on. What are reactants? What are products? And what do we do with these to represent them? So we're going to go over a lot of reactions in this chapter, but there's so many reactions. We have to find ways to categorize them, classify them, study them, and we break it down in a lot of ways. But what we're going to do in this class is what's the chemistry? Okay, so what are the chemical reactions? And what is just happening with the matter? How are the atoms rearranging? So if we get some general classes of reactions, then that can really help us go a long way. And then of course, experience becomes easier and easier when you see that was an acid-base reaction, that's an acid-base reaction. It's a little easier to identify after you've been seeing those. But let's start. How do we know that a reaction's even happened? What's the evidence? What can you say for sure? Wait a minute, something's going on here. Something's happening. Well, it'd be easy if you could just look at the individual atoms. Okay, the definition, if we're rearranging atoms, rearranging the matter, well, if I could just look at them, that would be easy. Of course, that's not always easy to do. So what we're talking about is, what is evidence that could indicate that a reaction has occurred? Maybe something has happened. But to prove it, we really need to analyze and say, no, matter has changed. This is something new. All right, so I encourage you, think about evidence. What evidence have you seen or thought about that proves a chemical reaction has happened? A couple examples, you've seen this in lab, solid formation, okay? Silver nitrate and sodium chloride, it formed a solid. You knew something happened, some reaction, because you saw a solid, or maybe a white or gray or maybe yellow solid form. That was evidence. Gas formation, okay? If you react and you see here the Alka-Seltzer giving bubbles, that's telling us gas is coming off. There's a reaction possibly happening. So let's go back here for a minute. Okay, we said solid formation, gas formation. You can take liquid water and you can freeze it and form a solid. Is that a chemical reaction? Or you can take liquid water and go to a gas. Is that a chemical reaction? Okay. The answer to both of those is no. What we're doing is just changing the state. That's a physical change, liquid water to gaseous water, liquid water to solid water. So what we're saying is a solid formation could indicate a reaction. Here, very likely a reaction happened because that's a red solid out of two colorless solutions. Here, gas bubbles coming out of this solid. That's very likely indicating a chemical reaction. Same thing, chemical reaction could be indicated by a color change, heat. You saw in lab, well, if you dissolve something, that's not a chemical reaction, that's a physical process that could give off heat, that could take in heat. Color change, you could dilute something. If you have lemonade and it's really a deep yellow and you dilute it with lots and lots of water, the color's going to change, but that's not a chemical reaction. So what we're saying here is this is the evidence that may indicate chemical reaction. So here's a summary of what we looked at. This one we don't really talk about in this class, the emission or absorption of heat. Sorry, we talk about this one, the heat we do. The emission of light isn't talked about very much in this class, but these others we will definitely do. All right, so that's the first part, is getting evidence. Something's happened, and now how do we represent that? How do we use chemical equations to tell us instead of words, right? This chapters before, you've learned naming compounds, ionic compounds, covalent compounds. These are lots of words, okay? Well, that can get a little tedious to talk about carbon tetrahydride plus oxygen gives you carbon dioxide and dihydrogen monoxide. Those are a lot of words. How can we simplify this to what are the reactants, what you started with, what are the products, what you end with, okay? So products are on the right, reactants are on the left. This is going to simplify these long descriptions of chemical reactions. We're going to see there's going to be a lot of information in these chemical equations. Physical state, that'll be helpful. I've already shown solid, liquid, gas. Those are our states. Here, if it's in water, so it's a mixture in water, it's an aqueous solution, AQ. So these are all going to be added to our chemical equations to give us more information on what's happening. So let's take a look at an example. Methane, again, look at this, the words here, okay? This is all that's used to describe what comes out of your Bunsen burner and has a reaction. Methane, or carbon tetrahydride, reacts with molecular oxygen on a gas stove to form carbon dioxide and water, could even say dihydrogen monoxide. Lots of words. Some of you are very efficient with words, right? You want to be efficient. Look at this, chemical equation. Formula, CH4, carbon tetrahydride. Formula, if it's oxygen, remember oxygen's one of the diatomics, we have to know that in writing chemical equations, O2. This is a good reminder, naming compounds. Carbon dioxide is a molecular or covalent compound. That's one carbon, two oxygens. Water is just the given name that you can memorize, or the systematic dihydrogen monoxide. Okay, we've got states. They're all in the gas state. So that's pretty good, right? Look at this. Lots of words, and then get down to the formulas, symbols, pretty quickly. What's our problem? What's going on here that we have to deal with? Okay, if we're thinking about matter and we're talking about transferring matter from the reactants to the products, we also have to remember our laws. Okay, and one law was the matter that you had on the left equals the matter you have on the right. That's conservation of mass. Well, look here, we have a bit of a problem. 2 oxygens, 1 oxygen, but we only have 2 on the left. So this is going to lead us to a really important part. If we're talking about the law, conservation of mass, we have to balance the atoms. That's what gets us to that law. So let's take a look at balancing. Of course, you can't create or destroy matter. Okay, so you can't just add some things in, delete some things. So here, that's a real problem. 2, 3, that's got to be dealt with. There's a couple of ways. Okay, we look at here, 4 hydrogen atoms, only 2 hydrogen atoms. So again, we can't destroy matter. So we have to account for this. We have to account for what's going on here, and that's by balancing. So if we do this correctly, we'll have the same number of atoms on both sides. And that's again all based on conservation of mass. This is really key. This next point is the most common mistake when balancing. Okay, balancing, you only change the coefficients. Those are the numbers out front. Okay, you do not change the subscripts. Okay, what this means, we actually talked about this in lecture. Okay, if we have the compound carbon monoxide and we need to balance it, we can't just say, well, let's balance it by giving a 2 there on the oxygen. These are definitely not the same thing. Okay, so if you want to add 2 oxygens, you can add a coefficient. That's the number out front, so that's 2 carbons, 2 oxygens. You definitely cannot add a subscript. Very tempting, don't do it. So for instance, we go back here, gives us 4 oxygen, so that's 2 times 2, and if we have 2 here, then we put a 2, so that gets multiplied by this oxygen. So that's 4 oxygen on the right, 4 oxygen on the left. We double check, we had more hydrogen on the left, that's 4 on the left. Now this 2 times 2, so if it, it's important to remember, maybe this would help. That's a molecule of water, so if you have 2 of them, you then have 4 hydrogen. So please, I encourage you, always check your work. You can put numbers out front and it looks like a balanced chemical equation, and if you don't check it, if you look here, they're checking each atom on the left, each atom on the right, then you'll know for sure whether you've got it balanced or not. All right, so here's some tips for you. First, you got to get the formulas. So that's a huge reminder. If you don't know your names, you don't know your diatomics, if you're having trouble, is it ionic, is it covalent, you've got to start there. You've got to have names that get you to formulas. Then a reminder, reactants, products, reactants on the left, products on the right. Go for it one at a time, okay? And start with something that's only in one compound on both sides. That's really simple because you can take care of that to begin with. Another tip, balance metals before nonmetals and balance single elements at the end. That's really nice because that doesn't change any other element. So wait till the very end, make the adjustment on that one. Don't forget, again, I already emphasized this, but again, only change coefficients. Definitely don't change subscripts. And then if you've sometimes there can be problems balancing. It can be challenging. You might have scaled up. If you look and you have 2 in front of one substance, 4, and you have 6 and 8, you need to go to the smallest whole number, so divide that down and then always check when you're finished. All right, so let's do some practice. Quick check, so go ahead and pause and work on these. Balance the 3, A, B, and C. Go for it. This is a critical reminder. You've got to be able to name. Chemistry is cumulative, that comes back in. So calcium carbonate, that's an ionic compound. This is a polyatomic from your list. This is an acid that comes from the polyatomic nitrate, which is NO3 minus. NO3 minus. Acids are when they have H plus, so that gives you the formula of nitric acid. Carbon dioxide we talked about, water, you probably know. And then if you know the ion for calcium and you know nitrate, then you should be able to write that formula. So we've got calcium carbonate, +2, -2. Nitric acid, nitrate's a -1, hydrogen's a +1. Carbon dioxide, molecular or covalent compound, same with water. And then this is another ionic compound. So what we can see here then is calcium, calcium. There's 1 and 1, so that's balanced. Great. Take a look. One thing we were talking about is balancing atoms. Well, if you look, if the group is the same on the left and the right, so this nitrate, you can just look at the group as a whole and say, I got 2 nitrates on the right, so I need to put a 2 out front here to get 2 nitrates on the left. When you do that, that takes care of your 2 hydrogens, and then we are accounted for the oxygens here, and so on. The next one, if you take a look here, we've got PCl3, which leads us to 3 in front of the HCl to give us 3 Cls. And if we got 3 H's here, that leads us to 3 H's here. And that is 3 F's, which takes us over here to double check. Oh yeah, we've already got 3 F's. So that's nice and balanced. So this other one I'm going to try and do underneath here so you can see. You may also just want to do a tally of the different atoms. Okay, so I'm doing on the left, there's 4 carbons. On the right, I only have 1 carbon. On the left, I have 10 hydrogens. On the right, I have 2 hydrogens. Oxygen, so you're keeping your tally marks, and you can see it's definitely not balanced. Okay, so you can start in a variety of places. I'll just go ahead and start with the carbon. So if I put a 4 here, then now that changes carbon to 4. If you take a look, that puts oxygen at 8, 4 times 2 oxygens, plus 1, so now that takes me to 9 oxygens. Okay, and go back here, 10 hydrogens, puts a 5. So now our hydrogens, take a look, we're doing pretty well. Carbons, hydrogens are balanced. That gives me 8, and that gives me 5. That gives me now 13. Wait a minute, 13, and if I'm looked over here, I leave oxygen because remember it's by itself. That's 2. How do I get that? Well, some of you would say, well, that's a fraction, no problem. That's 6.5, and 6.5 times 2, that gives you 13. Okay, we'll double check here. We don't write out chemical equations with fractions. So now we've balanced everything. Everything is good and balanced. Now to get rid of that fraction, we just multiply it all by 2. And so let's see if we can see this here. Oh, it's a little sloppy, but that's 2. That's the 13, because that was 6.5 times 2. 4 times 2 gave me the 8. And then 5 times 2 gave me the 10. So this tally can be really helpful as a tool to work on these. I encourage you to try it out. So now we're going to spend some time focusing on aqueous solutions. So this is the majority of what you're going to do. You're using water, and that's the substance that's given us life. So it's called the solvent of life, or water, aqueous solution. So it's a really important series of reactions and solutions to talk about. We got two things basically we're adding here. Okay, or two concepts that we're going to be talking about. The first one is solubility. Solubility is the question, does it dissolve? Okay, so when you saw this in lab, you would see a precipitate that doesn't dissolve. And you would see the supernatant, something did dissolve. Okay, so the first question, will it dissolve or not? And then what we're going to talk about right now, and you've probably heard this term, you need to get your electrolytes, or this beverage is filled with lots of electrolytes. The electrolytes, that terminology, is after it dissolves, what's in solution? Okay, does it dissociate? Okay, does it form ions? Or is it neutral? Okay, remember ions have charges. We got cations and anions. So some things dissolve as ions. Some things do not dissolve as ions. So that's the question we're going to focus on here. First is electrolytes. What's happening when things dissolve? We'll come back to this. Does it dissolve or not in a little bit. So sodium chloride, you've seen this. You've worked with this. Sodium chloride solutions, they are made up of ions that have separated. So there's no precipitate, no solid on the bottom. They're independent sodium and chloride ions. Another thing to note is we've talked about ionic compounds that are a little more complicated. Silver nitrate you used in lab, and you can see that's made up of ions as well. Silver plus, and these nitrates all stay together. Okay, so that has a charge as a group. That's why it's called a polyatomic ion. It stays together. It's a group with a charge. So that was silver nitrate that you used. That's what it would look like in solution. So here's our categories. If they dissociate, that means the ions separate. That's called a strong electrolyte. So sodium chloride, silver nitrate, these ions are strong electrolytes. Electrical conductivity is the result of freely moving charged particles. So if you think about tap water, it has ions in it. That's why this electrical conductivity can happen when an appliance is dropped in water, because there are ions there. So this is why, because of electrolytes. They move in solution because they're free of that. So example, light bulb apparatus. So if you look, pure water, so this isn't tap water, pure water is not made up of ions. It's a covalent compound. So it does not conduct electricity. There is nothing happening here. If you take sodium chloride, we just said it's made up of individual ions. Electricity can flow, light bulb is on, and that is a strong electrolyte. So things like sugar, sucrose will dissolve in water, but it does not have ions. It has neutral particles. So you put this on the light bulb apparatus, and sure enough, you get no bulb. So the key is you have to have ions. If you want the light bulb on, you just got to blend the bulb, nothing when there's no ions. Okay, so remember two things we're looking at. What's in solution? Are there ions or are there not ions in solution? And then does it dissolve? Okay, so some ionic compounds do not dissociate. So not all do, and you've seen this, right? Silver chloride you saw was a solid. It does not dissolve in ions. So that's going to get us to some rules to determine, will it form a solid, will it not form a solid? That's where we're going with this. So that's insoluble. This is a lot of terminology for it, but we call it a precipitate. In the chemical equation, it's an S for a solid. That's what's happening here with silver chloride. You also saw it for silver iodide. If it's soluble, that's the supernatant, it will dissociate in water and form the ions. All right, so these are pretty amazing reactions. So again, you can see if you form a solid, they come out of solutions, aqueous, aqueous, and it can be quite dramatic. That's really impressive, this nice yellow solid forming. So that's evidence chemical reaction has happened, and this is how we represent that chemical reaction. So that's the precipitate. Again, terminology, precipitate, solid, S, that's happening. What we're going to do is use a set of rules, okay? So remember, there's lots and lots of chemical equations. If we just classify them, if we take a look at series and say, in general, the rules are this, then we can know a lot about precipitation, okay? We'll be able to predict. So here's how these rules work. I've posted this on Canvas. In your textbook, it's a little more detailed, a little more pictorial, but I encourage you to try out these rules, okay? These are in order. So if we look here, number 1 rule, lithium, sodium, potassium, ammonium, these salts are soluble, okay? So if we think of something like sodium chloride, right away, in general, sodium is soluble. Now, if you took 5 pounds of sodium chloride and you try to dissolve it in, 5 mils of water, it wouldn't dissolve. But we're saying reasonable scale, sodium dissolves because of the rule, number 1 rule here. Okay, number 2 rule, nitrate, and this is acetate. These salts are soluble, okay? So if we take a look here, we've got lithium, we've got sodium, we've got potassium, we've got ammonium. Well, what if we did something like this? Okay, so what we're looking at here is the rules. Rule 1 doesn't apply. Lithium, potassium, sodium, ammonium, that doesn't apply. This number 2 rule says, yep, that's going to dissolve. That's aqueous. We already said this one over here is aqueous. Okay? Next rule. Now, look at this. Be attentive to these words. Silver, lead, mercury are insoluble. Okay? So, you've seen this in lab. Silver chloride is insoluble. It's a solid. That's because of rule 3. We don't have chloride anywhere up here. We have silver. Rule 3, silver, that's going to be a solid. Let's take a look at rule 4. Wait a minute. There's rule 4. Look at this, though. That comes after. So you go in order. Sodium chloride, rule 3 says it's insoluble. It's insoluble. You don't skip down to rule 4 and say, oh, it's soluble. No problem. Nope. Go to the rules in order. So in this case, silver chloride is soluble for that. It's also important to know these rules, the terminology. So carbonate, sulfide, hydroxide, phosphate, those are insoluble, okay? So remember, if it's insoluble, that's a solid. So if it's an exception to the insoluble, what does that make these 3? Yeah, if those 3 are exceptions, that's aqueous, okay? And our last rule with these specific substances, sulfate, these are soluble, okay? So that's AQ. And if it's an exception, these are solids. All right, so those are the extent of our rules. And then the last one, just throw in, well, if these don't apply, it's probably insoluble, okay? So I'll email you. I have an app that has, you can practice the solubility rules. That's really helpful. You can try that out. and see if that helps with these rules. So you can practice, test yourself, and so on. It's pretty handy. Okay, so how does this rule? How do these rules work? Does a precipitate form when aqueous solutions of Ki and PbNO3 are combined? So what we're looking at is ionic compounds. So we look over here, that's the cation. The cation's not going to combine with the other cation, okay? So our options are, does potassium nitrate form and does lead iodide form? Okay, so you need to go back to your rules or have your rules open and you can look and see, wait a minute, potassium was actually rule 1, it's soluble. Nitrate was rule 2, it's soluble. So that for sure is soluble. So that's not going to form a precipitate. The other one was lead iodide. If you look, rule 3 says lead salts are insoluble. So that's the one that we're interested in looking at, lead iodide, because the iodide rule doesn't come till after the lead. So if we look, looking about combination, which ones could form, this is the ones that we're thinking about. This is what we start with, lead nitrate, potassium iodide, and you're predicting what could form. Again, these are ions free flowing around. We know if they were solutions to start with, AQ, they're not going to form solids, so it's got to be the other combination. So you can see the other combinations we talked about, potassium nitrate, lead iodide. Guess what? These are just the potential insoluble products. How do we determine if it's a solid or not? You have to know the rules, okay? So insoluble is all about the rules. You've got to have these insolubility rules down to predict these. So if you take a look, the rules are listed here. What I really want to emphasize, if there's no combination that forms a solid, or their new combinations are soluble, there's no reaction. Nothing happens. Remember, our evidence to start this chapter was forming a solid was one example. Well, there's no evidence if there's no solid. So here, this case, the rules predicted, and here's the evidence, a solid forms. So go ahead and take a look and think about these examples. Think about switching the cations and anions, and then think about solubility rules. Will a solid form? Will it not form? Go for it. So remember here, sodium is going to be with nitrate. Cadmium is going to be with hydroxide. Look at the rules. Only the cadmium hydroxide will form. Magnesium acetate, potassium bromide, both of those are soluble, so no precipitate forms. Ammonium isn't a metal, but it's a cation, and barium and sulfate. Barium sulfate, example of an exception with that's a solid. And then lastly, lead again, we saw that before, lead iodide, sodium nitrate, that's the solid that forms there. So this is the first part, is just applying the rules. Can you predict what solid will form? What's the formula of the solid? You see all the formulas here come from the names, comes from the charges. And then we're going to do more. Okay, so really encourage you, start there, practice there. So what we have to do is write equations for these reactions. Okay, and well, you've seen equations now, you've balanced some equations, no problem. We'll take a look. There are actually 3 different types of equations that you can write for these precipitation reactions. So that's where we'll start with, is precipitation, and then we'll actually do this later as well for acid-base. So this is what we've focused on, is the molecular equations. And that's for everything. Every compound, that's the neutral formula. We want to see what's going on. Remember, our ions, this is the most difficult part in lecture and lab, is what are the charges of everything? So you have to show everything. Was it chloride? Was it sodium plus? Was it nitrate, -1? All of that, whatever's present, how many are present, you have to show that there. And then this net is we just care about what's actually happening. What's actually being changed? Where's the action at? Where's the chemistry at? That's what we care about. So I'll give an example of this. If we take a look here, silver nitrate, sodium chloride, silver chloride, sodium nitrate. So this, actually, you could all predict now. Okay, remember the questions before were, imagine that the cation and anion switched, apply the rules, sodium nitrate is soluble, silver chloride is not soluble. That's how you could predict the products. Okay, the next thing, so this was the molecular equation, that's what we've been seeing, but the next thing I want to talk about is the ionic equation. It is really difficult, but really encourage you to think about what compound is this, silver nitrate, what is it made up of? That's silver and nitrate. That all goes together. And then you have to continue to separate everything. So if you look, I'm just doing the reactants here. But if it's an aqueous, you have to separate these as well. The exception is if it's a solid, it stays together as a solid. So take a look here, the complete ionic equation. Separate ion, separate ion, separate ion. All here, this stays together, and these are separate. This terminology spectator means sodium's on the left, sodium's on the right. It's not doing anything. It's just watching things here. Nitrate, it's not doing anything. It's just hanging out. Okay? So just like in math, if you have the same variables on opposite sides, you get rid of them. You cancel them. That takes you to the net. So this is where the chemistry is at. This is where all the action is. It's just around the silver, just reacting with the chloride to get the solid silver chloride. So go for it. Now you're starting from the very beginning. This is the word, so you have to go from name to formula, do the molecular equation, complete ionic, and net ionic. Again, I can't reiterate enough, this is, I think, one of the toughest sections of Chem 152. If you look, this is a lot of work just to get from here. Okay, so looking at it, lead 2 nitrate, that's the name of this compound. From the naming chapter, nomenclature chapter, we need to be able to get to the formula. Lithium chloride, we need to get here. Then we need to look and say, what are the products going to be? Okay, that's where then we crisscrossed again. Lithium with nitrate, lead with chloride. Then we had to look at the rules. Lead chloride's a solid, lithium nitrate dissolves. And then lastly, where we started this chapter, we had to balance. Okay, so you balance, and now you've got the molecular equation. Here's the big one, getting to the ionic equation. Okay, so here, have to recognize that that's lead 2, Pb2+, and look how this happens. 2 nitrates are present, so the 2 comes in front as a coefficient and tells you there's 2 nitrates. This 2, because it's a coefficient, it's not a subscript, it gets distributed to both of them, so that's 2 lithium, 2 chloride. Solid stays together, and this 2 gets distributed to this and this. So lithium nitrate. So then you can look and say, wait a minute, which ones are the spectator ions? That means they're the same on the left as the right. That's lithium, get rid of it, garbage, don't need it. Nitrate, get rid of it. And now you've got the net ionic equation. It's just the lead, the chloride, that's what we've got here. So precipitation reactions, solubility rules, all of that is kind of the bulk of the material to learn here. That concludes that section, but we're going to use some of these same principles in the acid and base section. Okay, so a review, acids and bases. Acids have H+, and they got a sour taste. Maybe you've seen some of this terminology before. They can dissolve some metals. There's a lot of superhero or crime. They had some acid in the jail, dissolved the bars, so that's dissolving metals. Bases are OH, that's our polyatomic ion hydroxide, and they're bitter, slippery. If you clean your oven at home, you most likely use a sodium hydroxide, so it's really slippery. I hate doing it. It's the worst feeling. I just don't like that feeling on my hands. So here's some list of some other substances, acids and bases. So acids on the left, bases on the right. I mentioned the sodium hydroxide, the oven cleaner, and you can see some other ones. Acetic acid is vinegar or balsamic vinegar. That's fantastic. So that's the formula there that comes from that acetate polyatomic ion. So acids and bases react. We're going to come back and do more on acids and bases, but here I just want to introduce that acids and bases react and they neutralize. So the big take home here is if it's neutralizing, you want to be thinking that's forming water. Okay, that's the neutralization reaction. So, which is making sense because we've got an H plus from the acid, OH minus from the base. You put those two together, that gets you your water. Okay, so that's your H2O. So in general, it doesn't matter what acid or what base you have. What we're saying is it's going to form the water and it's going to form some salt. Well, that can be a little misleading. Just note that salt doesn't necessarily mean sodium chloride. It means any ionic compound. So that's really key when we think about this water and a salt. And here's just the terminology again. This is very general, ionic compound. So take a look. This looks very familiar. Write a balanced molecular equation, a total ionic equation, and a net ionic equation. So this is an acid-base neutralization. However, we can still do the same thing. So hydrobromic acid, that was the naming chapter. That's HBr. And calcium hydroxide, that's our base. So that's our calcium hydroxide. And if we see an acid plus a base, we should think immediately what's going to form. Okay, it doesn't tell us our products. We have to predict our products. Acid plus base equals a water plus a salt. Okay, in this case, the salt's going to be made up of this metal, calcium, and this nonmetal. Calcium's plus 2, bromide's minus 1, so that means the formula for calcium bromide is CaBr2, and that's in solution. Okay, so we have a molecular equation, but what do we have to take into account? Yeah, if we just get the formulas, that's step one, we've got to then balance it. So if we take a look here, we had 2 bromides, so we need 2 HBRs. If we have 2 H's there, we've got 2 H's there, we need 2 here. So that's the first part, okay, the molecular part. The next part though, we've got to convert all of these to ions. So remember the acids form H pluses. There's the bromide. Aqueous, we've already done this. Calcium hydroxide. This is not aqueous, so water stays together. H2O stays together. This ion is separate. These ions are separate. We're not done. That's the molecular, the total ionic. Remember the net gets us, we get there by crossing off the spectators. And look at this. This looks very different. The net, acid, H plus, OH, base, water, and if that's all 2, 2, 2, 2, you can simplify that down to 1, 1, 1. So that's unique. Acid base always comes down to this net ionic equation. So we've done precipitation reactions. Now we just quickly did acid-base reactions. And one other piece that we're going to add are gas evolution reactions. Okay, so we've got combination and form some gas. My CHEM152 class did this earlier in the semester. You make this gas and it is awful. It smells like rotten eggs. It is terrible. You never forget it. That's a gas formation. You see bubbles form. You smell the gas. That's a new chemical reaction, that's evidence, right? If you smell that, that is evidence something is happening. What we can see is some of these also have what's called a decomposition reaction, okay? That something is formed and it's not stable, and then it breaks up. So if you see here, H2CO3 forms from this reaction. It is not stable. Now it breaks up and bubbles and forms gas. So this is a gas evolution reaction. So the real take home here is gas evolution is an aqueous plus an aqueous gets you a gas. Remember, precipitation was aqueous plus aqueous gets you a solid. And acid plus base, what did that give you? That was that water and a salt. So we're just classifying general reactions, generally acids and bases. So, you know, whether it's hydrochloric acid, hydrobromic acid, this is the pattern it follows. Precipitation reactions, this is the pattern it follows. And now we're looking at gases. This is the pattern it follows. It doesn't matter if it's H2S, CO2, SO2, or NH3. Remember the pattern? Aqueous plus aqueous, and then somewhere in here there should be a gas. So that's gas evolution. Another class of reactions. There's a lot of reactions that were thrown out here in this chapter. Another class of reactions is electron transfer. Okay, so remember, electrons are negative. That's really key. We're transferring negative electrons, and here's how we can tell if one has occurred. A substance reacts with molecular oxygen. That's our combustion reactions. Remember, we had methane plus oxygen forms CO2 and water. So if it reacts with molecular oxygen, that's oxidation reduction. This was experiment 6 for CHEM152L. When you looked at the experiment of magnesium plus oxygen, it formed a magnesium oxide. That's a redox reaction. If a metal reacts with a nonmetal, so if elemental sodium reacts with elemental chlorine, that is a redox reaction. And the key takeaway is that electrons are being transferred. That's what it means to have electron transfer reactions. So we've got one other class of reactions, and that's combustion. So we've already looked at this, and I just mentioned methane. That's an example of a redox reaction because it combines with oxygen. So it combines with oxygen, and in our cases, the examples that we're doing, it could be a carbon-hydrogen compound, carbon-hydrogen-oxygen compound, but the products are CO2 and water. So acid-base, products, water and a salt. Combustion, the reactant is oxygen, and products is CO2 and water. So these are trying to classify or putting in groups all of these reactions based on the chemistry. That's what we've just done so far, is what's chemically happening. Now we're coming to the end of that. We're summarizing based on the chemistry. So it's a lot, okay? Now we can base on classifying reactions by what atoms do. That's what we're going to do here in this last few series. I think this is a little bit easier to see because it's hard to remember. Is that an acid? Is it a base? What are the solubility rules? That's a lot of chemistry to remember. But you can see this. This is like Lego pieces. Are these pieces combining? Are these pieces breaking up? Is there a single displacement? Is there a double displacement? Okay, so this is definitely, I think, keep track of this with easier to see what the atoms are doing. So the first one, synthesis or combination. So take a look. We have 1A, we have 1B, so there's two things on the left, and we have one thing on the right. So I gave this example a little bit earlier. This is elemental sodium, which is a metal, elemental chlorine, which is a nonmetal, and it combines to form an ionic compound. So this is a combination reaction. Guess what? Remember, the chemistry was another way we were talking about reactions. It's also a redox reaction. Okay, we went from neutral sodium to sodium plus, neutral chlorine to chloride. So we went to the ions. If we went to the ions, That means a transfer of electrons. Oops, sorry about that. That's neutral sodium. That means we had a loss of electrons there. And if we went to chloride, that means we gained an electron there. Decomposition. Okay, so if we're combining, two things go to one, you can imagine then if you're decomp or breaking apart, you go from one thing to two. That's a decomposition reaction. So here you can see water being separated out into hydrogen and oxygen. That's a decomposition reaction. Single displacement. This is kind of an awkward example, but this is the third wheel. A and B and C are together, and then A steps in and B gets separated. Very strange, uncomfortable. Well, metal pops in and hydrogen gets out on its own. Single displacement. Double displacement, also called metathesis. Maybe this is even weirder, I don't know, but if you think about this one, double date. A, B, C, D, they go out on a double date, life is good, and realize, wait a minute, I'm much more interested in the other person. Okay, so take a look. The metal, C, combines with the nonmetal and the other substance. The metal A combines with a nonmetal and the other substance. So this is double displacement. This is precipitation reactions that we've been seeing. Lead, more interested in combining with chloride. That forms a solid. That's precipitation. That's also a double displacement. So you can see we can comment on reactions based on the chemistry. We can also comment on based on how's it rearranging. Is it a double displacement, single displacement? So you can see this is a lot of chemistry in this chapter. Please come to office hours, send email questions if you want to go over these things.